Hello. In the previous video, an equivalent of this image was shown. It was a chip engraved on a film made of a flexible plastic material with conductive tracks. This technology is known by the acronym COF, which is an abbreviation of chip on film. The small circles in black correspond to test points. They are not directly accessible because they are covered with an insulating material which must be removed if we want to access the conductive part. To know the name and the function of each test point, it is necessary to note the name of the chip registered on the COF and to find its datasheet. Here, we are interested in the chip that drives the rows called gate driver. The name of each test point is given in abbreviated form whose meaning will be detailed in this video. We see in this example the location of two COF of gate driver placed on one side of the screen. The plastic material used is made of a polyimide, which one of its characteristics is to be thermostable. It does not vary during 1000 hours at 300 degrees Celsius or during 10 hours at 400 degrees. As it is flexible, this technology is also called chip on flex. Some screens, especially those of the last generation, do not have a COF gate on the sides. This does not mean that the screen does not have a gate driver. On the contrary, the chips exist and they are integrated directly into the panel as for TFT transistors or storage capacities. This technology is currently favored in the manufacture of screens and it has several names. We find COG, which means chip on glass, GIP for gate driver in panel, or GOA for gate driver on array. The gate drivers are used to drive the TFT through their gate. They control the passage or not of the voltage that feeds all the gates that are on the same line. The transistors are in on state when their gate is supplied with VGH. They are in off state if their gate is subjected to VGL. A technical precision concerning the mode of manufacture of transistors TFT, which is the acronym of thin film transistor. There are mainly three modes of manufacture of TFT. Each technology has its advantages and disadvantages. The most widespread and oldest technology uses hydrogenated amorphous silicon material. Another technology, called EXO, which is the abbreviation of materials used in the manufacture of TFT, and which are indium, gallium, zinc, and oxide. The advantage of this technology is that this alloy allows more light to pass through, which reduces energy consumption by reducing the light intensity of the backlight. On the other hand, the size of the TFT in EXO are smaller, what allows to put more pixel in a panel where an improvement of the display resolution. The third technology is called LTPS, which acronym of low temperature polycrystalline silicon. LTPS has the same advantages as EXO, and in addition it allows to integrate the electronics with each pixel. Now, we are going to tackle the heart of the matter, namely the internal electronics in a gate driver chip. This chip contains a succession of electronic functions cascaded one after the other. Thus we find a shift register, a logic control, a level shifter, and a buffer. The shift register is an assembly of several electronic devices called a flip-flop. There are several models. Here will be used the flip-flop D. It has two inputs. A first input for the data named D, like data, and a second input, T, for the time controlled by a clock signal. The D flip-flop has two complementary outputs, one called Q, and the other Q bar, which takes the inverse value of Q. The operation is relatively simple. The value present at the input D, 0 or 1, is transferred to the output Q under the control of the clock, T. Depending on the setting of the flip-flop, the exact moment of transfer is made either on the rising or falling edge of the clock. The rising edge corresponds to the moment when the clock signal passes from 0 to 1. The falling edge is the opposite. Here is the table of operation of a D flip-flop. When the input D value is 0, the up arrow means rising edge of the clock. The output Q will be equal to the input, so 0 and Q bar is the opposite, it will be 1. When D is equal to 1, Q will be equal to 1 and Q bar will be at 0. The configuration of the shift register is done according to this diagram. Several flip-flops are connected in series. The output of each flip-flop is connected to the input of the next flip-flop. The information or data enters serially into the first flip-flop and leaves serially from the last register. The output of each flip-flop enters the next flip-flop, but the information also takes a second path which is parallel to the outputs of the other registers. Q1 coming from the first flip-flop constitutes the input of the second flip-flop. The output Q2 will be the input of the third register, and at the same time it will constitute an output which will go up in parallel to Q1. And so on. This assembly allows to store a binary data. In the gate driver, the D of the data will be the signal that allows the scanning of the lines to begin vertically. In short, it is noted STV, which is a contraction of start vertical. It can be found under the abbreviation VST, which is an inversion of the previous words, which gives vertical start. STV or VST is the V-sync, which is abbreviation of vertical synchronization. For the clock signal, the T is replaced by CPV, which is a contraction of the words clock pulse vertical. The following animation shows how the information flows from one flip-flop to another in series, but also out of each flip-flop in parallel. The shift register used in gate drives is often bidirectional, i.e. the information can flow from left to right or vice versa. STV is the signal of the beginning of the vertical scanning of the frame. CPV is the clock signal, which allows to synchronize the output of the data of each flip-flop in a successive way. On datasheets, there are different ways to specify the direction of operation of bidirectional registers. For example, for STV, which is the abbreviation of vertical start, we add a number to STV. STV1 will indicate the direction of the scan from left to right, and STV2 for a scan in the opposite direction. We can find another denomination like SVIO or SVOI. SVOI is the abbreviation for start vertical input output, i.e. a scan from left to right, and SVOI is the start vertical output input for a scan from right to left. Another term, DO, for data input output, or DOI, for data output input. On the datasheet, we can find the inscription RL, which is an abbreviation of right and left. The gate drivers used in LCD have the characteristic of having a bidirectional shift register. Depending on the configuration of the RL pins, the scan will be different. For example, if the RL pins are in high mode, the scanning direction will be top to bottom. Or written in another way as shift right. If RL is in low mode, the lines will be scanned in the opposite direction from bottom to top. This is why an image can be inverted depending on the setting of the RL pins. Here is an example with 3 driver gates in series. The direction of the scan is determined by the configuration of some pins. On the datasheet, it is necessary to look for the inscriptions RL for right-left and, or, the inscription UD for up-down. In this example, the direction of the scan will be either from STV1 to STV3, i.e. from top to bottom. Or in the opposite direction, from bottom to top, i.e. from STV3 to STV1. This animation shows the appearance of the image according to the direction of the scan. In the conventional direction, the scan is from left to right and from top to bottom. This scanning direction is determined by the configuration of the pins UD for up-down and RL for right-left. In all, there are 4 display possibilities depending on the combination of the up or down state of the different pins, but there is only one state that allows for a correct display, i.e. in the right direction. When troubleshooting an LCD TV, for example when installing new software, the picture can be reversed. Without intervening on the hardware, it is possible to correct this problem by intervening on the software of the television using the remote control. To do this, you need to access the service menu and then, depending on the model of the television, find the mirror mode entry. By changing the value from on to off or the other way around, the image will be put back in the right direction. For other brands, you must first find MRT option and then find the HV flip function, which allows you to control the direction of the display. In the animation that we have seen before with the shift register lacks other stratum or layer of material that composes the gate driver, and that will allow to supply the TFT in panel with VGH and VGL voltage. We recall that the TFT transistors do not work with a digital signal and need an analog voltage. VGH and VGL are the analog voltages that allow to activate or deactivate all the transistors putted on the same line. VGH and VGL are provided by the T-Con board thanks to a DC to DC converter. VGH is the acronym of voltage gate high. It is the voltage of starting of the TFT transistors, from where the abbreviation V on is sometimes used. VGL is the acronym for voltage gate low. It has a negative value and is used to turn off the TFTs, hence the other name V off. The names and inscriptions of VGL and VGH vary from one TCON board to another. We can find V on and V off written with or without an E at the end. Sometimes is added G in front of the word off or on. G corresponding to the first letter of the word gate. Other inscriptions to designate the VGH and the VGL, we can find VEE, corresponding to VGL or VEEG. VGH can be written VGG or VDDG. We saw previously in the block diagram of the gate driver the existence of a logic controller circuit. The latter is constituted by an assembly of several logic gates. At the electronic level, the various logic gates are composed of transistors. For the understanding of the subject, a short reminder on some logic gates is necessary. The yes gate is the most basic logic gate. It is also known as a buffer. Its function is to simply copy the state of the input bit to the output bit. So if the input bit has the value 0, then the output will also have the value 0. If the input is equal to 1, the output will also be equal to 1. In a NOT gate, the value of the output bit is the inverse of the input bit. On the diagrams, to differentiate this gate from the yes gate, has been added a small circle in front of the triangle. For the result, if the input is equal to 0, the output will be equal to 1. If the input is equal to 1, the output will be equal to 0. In a logic gate AND, there are two inputs and only one output. The output value will be equal to 1 only if the two input bits are equal to 1. In other cases, the output will be equal to 0. The inverse of the AND function is the NOT AND gate, abbreviated to NAND. This gate corresponds in reality to an AND gate followed by a NOT gate. This allows to find the inverse of the AND gate. The logic circuit of the gate driver is made as follows. According to the number of shift registers are placed in series as many NAND logic gates. There are two successive layers of interconnected NAND gates. The first series of NAND gates is under the control of the OE digital signal, whose role will be seen later in this video. In front of the output of the OE signal is placed another logic gate NOT which will invert the signal. On the second line all the NAND gates are under the direct control of a digital signal called XAO, the meaning of which will also be explained later on. For a normal operation of an LCD screen, the OE signal is at a low level or 0 and XAO is at a high level or 1. At the first sight of this diagram we can wonder why to have complicated the circuit to finally find at the output of the NAND gates the same values as at the output of the shift registers. There is a reason for this which will be developed in a moment. Let's continue with another element of the gate driver block diagram, which is an electronic circuit called a level shifter or voltage level translator. The principle of this component is to make compatible circuits working with different logic levels. For example, a first circuit noted 1 provides a digital signal of 3.3 volts. The second circuit noted 2 works only with a logic level of 5 volts. To make the two circuits compatible, the level shifter will raise the voltage from 3.3 volts to 5 volts. The reverse operation is possible. The clock signal CPV of the shift register is transformed by the level shifter into CKV. It is the same clock signal but with a higher digital voltage value. CKV is an abbreviation for vertical clock, the clock that controls the vertical scan. The level shifter chip can be integrated into the gate drive chip, or integrated into the TCON microprocessor. It can also be found as a separate chip on the TCON board. To locate it on the TCON board, look for markings such as CPV, CKV, STV or VST, which mean the same thing. Here is an example of a level shifter chip on this TCON board. At the input of the chip you will find the terms STV and CPV, there is also the term OE. At the output of the level shifter, the conductive tracks are engraved on the back of the board and then reappear at the test points which are directed to the connector of the screen. We can see the term CKV, but there are also other terms such as CKVB and STVP. Note that on this board the VGH and VGL are labeled V on and V off respectively. The level shifter transforms CPV into CKV. The STV signal is transformed into STVP. CKV and STVP are the same signals as CPV and STV respectively, but CKV and STVP have a higher voltage value. From this level shifter will come another clock signal, which is the CKVB. This signal is the inverse of CKV. It is also used to control the gate of TFT transistors. The B that has been added to CKV comes from the word bar because the inverse of a value is mathematically noted by a bar above the letter that represents it. Here is a chronogram that represents the correspondence between CPV or CKV and the output signal of the gate driver. At the rising edge of the first clock pulse, the first output of the gate driver called G1 is activated. Note that the activation time of a line is equal to the duration of a clock pulse, which includes a high clock level and a low clock level. At the second pulse of the clock still on its rising edge, the second output of the gate driver G2 is activated while the previous output G1 is stopped. The same process will take place successively until all the gate driver outputs are scanned. The disadvantage of this process is that there is a certain waiting time between the activation of each output. To shorten the scanning time of all the lines, we added another clock signal with a period inverted with respect to CKV, called CKVB. The principle of operation is as follows. Instead of waiting for a new signal from CKV, the second output G2 is connected to the CKVB signal. Thus, the two clocks work at the same time but with a shift between the rising edge of each of the clocks. With this organization, CKV will drive the odd lines while CKVB will drive the even lines, thus saving time to scan all the outputs of the gate driver. When there are several gate driver chips, for example 3 chips that control each 360 outputs in horizontal lines, we assign to each gate driver a pair of CKV and CKVB signals and we add a number 1, 2, 3, to identify them. Each clock will control 180 lines. CKV 1, 2 and 3 be assigned to the odd lines. CKVB 1, 2 and 3 will be assigned to the even lines. We find the terms CKV1, CKV2, CKVB1, CKVB2 in Samsung panels, but other companies use other terminology to designate the various clock signals. In LG panels, the terminology used is CLK1, CLK2, VGH odd, VGH even. In the AUO panel is used HC1, HC2, LC1, LC2. HC is an abbreviation of high clock and LC low clock. The level shifter can be located both before and inside the gate driver. Here it will allow to transform the digital signal VDD and VSS into VGH and VGL. If the output of the logic circuit is at a high level or 1, it is translated to VGH. If the output is at a low level or 0, it is translated into VGL. The last step in the gate driver, before the VGH and VGL voltages reach the TFT transistors, is their passage through a buffer. The latter is a voltage follower circuit whose purpose is to separate the circuits present in the gate driver from the TFT transistors and storage capacities that are inside the panel and constitute the load to be supplied with voltage. We now arrive at the OE signal, which is a contraction of the words output enable. We see that this signal is placed downstream of the output of the shift registers. The role of the OE signal is to control the activation time of each output. Here is the reason. In this illustration, in green is represented the voltage VGH which feeds the gate of transistors placed on the same line. This conductive line is not perfect because of the parasitic effects, which are the resistance of the conductor and the presence of a parasitic capacitor between gate and source called here, CGS. The resistor and the parasitic capacitor constitute an equivalent of RC circuit low-pass filter. The electrical pulse VGH that we call gate pulse must travel a certain length from left to right. With the parasitic effects of conduction, the VGH signal will undergo a distortion on its rising and falling edge. We see the signal at the beginning of a line is not exactly the same at the end of the line. This distortion can be seen especially with large screens for an obvious reason of the longer line to cover. This defect of conduction has consequences on the quality of the display. On this diagram is represented the progression of the display of the image line after line. At the time of the activation of the first line, the data of the image is delivered to the corresponding line and with the adequate time. Then it is the turn of the second line to be activated with VGH while the previous line is switched off with VGL. The coordination process between the lines in the data will continue successively until all the lines are scanned. It is the T-Con board that ensures the coordination between the activation of a line and the delivery of the data to the corresponding line. As a reminder, T-Con is an abbreviation of timing control. In practice, because of the parasitic effects of conduction, the VGH signal undergoes a distortion and a shift in time. Line 1 will not stop at the desired time, and the data which are intended only for line number 2 will also be displayed on line 1 since it is not stopped. This will create an abnormal display of the image. This phenomenon is called crosstalk, to say that the data from line 2 will also reach line 1 since it is not yet stopped. In this animation you can see the coordination that exists between a line that is activated and the data that reaches it. After receiving the data, if line 1 does not stop in time, this is what happens. The data from line 2 will also be delivered to the first line, but this data was not intended for it. This is the phenomenon of crosstalk and leads to an abnormal display. To correct this crosstalk problem, we introduced the OE signal for output enable. When this signal is at high level, it stops all the lines that are active. When unfortunately the operating time of two lines overlap, OE allows to block this zone. This prevents the data from being misdirected. This is equivalent to controlling the operating time of each line. The width of the OE pulse is variable and only acts on the lines that are active at the same time. The XAO signal is a signal that allows to detect the extinction of the screen. This signal has been added to deal with the problem of image retention even after the screen is turned off. When the screen is on, the XAO signal is at its high state. When the screen is turned off, it goes to its low state. This causes all the TFT transistors to be turned on at the same time, and it allows all the capacitors of the screen to be discharged. This is why the XAO signal is assigned a reset function. We see on this chronogram, although there is an OE pulse, there is no action on the state of the line because XAO is higher than OE and does not allow it to block the operation of the TFT. As another name for XAO, we can find on the datasheet the name XON. On the electronic side, XAO consists of a voltage detector. It monitors the VIN voltage. When the latter falls below a certain threshold, as when the screen is turned off, XAO emits a reset signal. In this assembly, there is a voltage comparator and a MOSFET configured in open drain because its source is connected to the ground. This diagram shows the various circuits that we have seen. At the beginning, there is the shift register with the different inputs, CPV or CKV, STV or SVIO and SVOI, LR and UD, followed by the logic circuit composed of NAND gate, logic voltages VDD and VSS, and the signals OE, XAO or XON. Then comes a level shifter which translates the digital signal into an analog signal made of the voltage VGH and VGL. Last step, VGH and VGL pass through a buffer to be distributed to the TFT inside the panel. We arrive at the end of this video with this animation that summarizes the mode of operation and control of the pixels by the gate driver through the various electronic circuits that constitute it. Goodbye and see you soon.